So today we discuss Gauss's law, okay, and previous class we discussed the definition of Gauss's law, okay, some flux concept here, and flux positive, flux negative, and zero flux, okay. So today we solve first two numerical, basic numerical, NCERT numerical mainly we solve, okay. So first numerical is NCERT numerical. The given a cylinder, that is cylinder given actually, okay, and an electric field in that direction, straight line electric field, okay, and calculate total flux, calculate total flux crossing by the cylinder, okay. So first we see that consider the three surface actually, the front of cylinder, and that is that behind this is also a circular, okay, and this is a curved surface, okay, front and that behind, okay, at top or bottom you can choose any one of say top bottom bottom top, doesn't matter, and that's a curved surface, okay. So see that consider the three faces, front, back, or top or bottom, and there is a curved surface. Okay, so that there is a area of the curve, small area. The first, okay, choose that this area. This area is called A1. Okay, so know the area vector always normal to the surface. Sorry. So normal to the surface. Yes. A1, okay, delta A1 normal to the surface, and electric field in that direction, that is given actually, okay. Then you choose the electric field that is equal to 1.0. So here, and electric field SI unit is Newton per Coulomb, some 1 Newton per Coulomb electric field, okay. So electric field in that direction. So phi of A1, that the angle, this angle is 180 degree, and that is equal to E dot delta A1, okay, and the angle between these two is theta is 180 degree, okay. So that is we get E times delta A1 cos the magnitude of these two, theta is 180 degree. So we get a cos 180 is minus 1. So E times delta A1. Total flux. Okay. There is a three surface. There is a left faces or front faces. And here that surface 2. The area vector now normal to the surface actually. That is a A2 delta A2 area vector. And electric field, you see carefully, in that direction is electric field. Okay. E, and that is a curve, okay, actually that is 3D surface, okay. So that delta A2 actually they coming out from the board, actually this coming out of paper in that direction, and that angle is 90 degree actually, okay. So phi of A2 that is equal to E and delta A2 cos 90 degree. So cos 90 is 0. So 0 multiplied by anything, that is to get a 0. Okay. So that is equal to SI unit is Newton per Coulomb meter square. Here we suppose 0 Newton per Coulomb meter square. And that is a third surface. Means a third surface, see E3 in that direction actually, delta A3 in that direction, and electric field also in same direction. So that theta equal to 0 degree. So phi 3 E vector dot delta A3. So E delta A3 cos 0. We know the cos 0 1. So E dot delta A3. Okay. So total flux is algebraic sum of three fluxes. Okay. So algebraic sum of three fluxes are phi equal to phi 1 plus phi 2 plus phi 3. So what is the value of phi 1? So phi 1 we get minus E times delta L1, and phi 2 be the 0, and phi 3 is the E times delta A2. So delta A2. And you see that if that is a diagonal cylinder, we know the front and the back, these two are look like a circle, and these are the same, okay, same area. So A1 equal to A2, A1 equal to A2, so they cancel each other because the E are the same, that is a total flux 0. So total flux 0 signifies that these surface, actually these closed surface, actually they do not bound any charge, okay, any no charge bounded surface, okay. Net charge with a 0 actually means net charge enclosed by the surface is 0. Describe net charge enclosed by the surface is 0. Okay, so no charge enclosed by the surface. If you are writing there is a suppose 5 coulomb charge positive, and also there is a 5 coulomb charge negative, so that's why total charge will be 0. We added these two charges, so net charge will be 0. If there is any charge inside that curved surface area or closed surface, but there is a net charge with a 0 in that case. Okay, and here you see that a similar condition here, look like this diagram previous class, that is the total flux be 0 means so no net charge enclosed by that surface, that 3D object actually. Okay, now next problem question number 2 from NCERT. The problem number 2 from NCERT, a 3D diagram. You see that is X, Y and Z. There is a 3D box. Now look like this, a 3D box. That's a 3D box. Okay. So non-uniform electric field is the non-given, actually given is non-uniform electric field. Okay, that is E, that is equal to 3.0 xi cap plus 4.0 j cap. Okay, that is a Newton per coulomb. Electrical is given, and pierce the Gaussian surface. Here, the Gaussian surface, or Gaussian cube, actually Gaussian cube. Calculate the phi at all faces. Calculate phi at top, bottom, not sorry, actually not bottom, top, left and right. Means actually we want to calculate a phi in right surface, left surface and top surface. Calculate a phi. Okay, that is a cube actually. Okay, so here the givens x equal to 0 meter, and that is x equal to 3 meter, that is given. Okay, So if I choose the electric field here, you see that here E, suppose in that direction, actually E in that direction, that is a two component or two parts of E electric field is X part, that is a EX, and that is a Y part, that is EY. Okay. So if I choose the right side faces, right faces, these right faces, and you see that is consider small area, that is area is called delta A, and that area is the vector in that direction. So you know the area is normal to the surface, area vector, that is A area vector, and EX, actually component of EX part is EX in same direction. Okay, so if both are in same direction, so that is equal to E right side, or called EX part. Okay, EX. So phi of right face, that is equal to closed integral, surface integral obviously, Ex dot delta A. Okay, that is also a right faces. Okay, this equation we get from here. Okay, actually this equation phi equal to closed surface integral E dot delta A. Now so dot product means here that is a Ex delta A RF cos 0 degree. So you know cos 0 be the 1. So right side E and A are both are in same direction. So that is cos theta equal to 0 degree. So Ex integral of DARF. Okay. Here another point is given here. See that the diagram very carefully. That is a cubical box, and that starting point is x equal to 0 meter and ending is x equal to 3 meter, and that length, okay, from 0 to sorry, that not from 0. Okay, actually that is a 0 0. Okay, sorry, that is a 1 meter. Sorry, that is 1 meter. 1 meter to 3 meter, actually sorry, that is given is 1 meter, 1 meter to 3 meter. So length of cube is 3 minus 1, that is 2 meter. So length of cube is 2 meter. So Ex that is given, that is 3.0 x I cap plus 4.0 j cap times, and dA, integration dA means A. We know that that is integration of dx is A. So that is dA also we get integrate from A. So that is equal to 3.0 x I cap plus 4.0 j cap, and A be the area. Area is the surface, okay, right face. That is a square. So area is 2 times 2, 4. Okay, 4 meter square. But area is a vector. So that is a x direction means 4 I cap. So x direction represent I cap. So y direction represent j cap and z direction represent k cap. So 4 I cap. So you know that dot product I cap dot I cap, that is we get a 1. J cap dot I cap we get 0. So that is cancel. Okay, so we get 3 times 3.0 x times 4 I cap dot I cap from vector algebra. You know that is I dot I unit vector is 1. That is 3.0 x cos 4. So what is the value of x? That's important here. Okay, no, don't know, but actually we consider the right faces. Okay, right faces, the value of x is 3 meter. So put the value of 3 here. So 3 times 4, that is 936, and that is a Newton per coulomb meter square. The answer, right faces. So what is the value of left face? Left face means these face. Okay, behind that face, these faces. So actually see that that is a minus x direction area actually. Okay, that is area is minus x direction. You see that carefully. Area is minus x direction means minus I cap. Okay, so that a similar values here we get is minus I cap. Okay, so phi of left face is that is same integral formula ex dot d a left face. Okay, so ex in that direction, df in here that direction, so that a cos 180. Okay, so that is a minus actually. So we just multiply that left faces formula. So we get here that is 3.0 xi cap plus 4.0 j cap, and the left faces represent 4 minus I cap. So here 4 3 is a 12 minus 12 x I cap dot I cap be that 1. So that is minus 12. What is the value of x? Here in left faces, so you know the x equal to 1. So 12 times 1 means minus 12 uh, Newton per coulomb meter square. Okay, so the last part is top part. Okay, so see the top part very carefully. The top part here actually electric field in EY. Okay, so actually area vector also in that direction. Okay, EY both the area and A also the same direction. So calculate these two. So if I calculate these two, both are top faces actually. Okay, so then the top faces both are same. So EY, so we get that is EY top, and that is area also same. That is also the cos 0. But the phi of top faces, top face, that is EY delta A top face electrically. So that is 3.0 x I cap, 4.0 j cap, and top face means same area but top side means a j cap direction actually. So positive j cap, 4 j cap. So I dot I 0, so j dot j 1, so 4 4 is 16, and j cap dot j cap is 1, so that is Newton per coulomb meter square. That is the top face, faces flux. Okay, the solving numerical is very easy if you know the concept. Okay, now the next topic we discuss the Gauss's law, and the derive the Gauss's law. Okay, okay, so the Gauss's law actually, Gauss's law say that is epsilon naught times phi, okay, that is equal to charge enclosed by the surface. That is the Gauss's law formula. Actually net flux phi, the net flux phi of an electric dipole of an electric field, sorry, electric field, and through a closed surface, mm, closed surface to the net charge, to the net charge U E N C enclosed, that is enclosed by the Gaussian surface, that is enclosed by the Gaussian surface. Okay. So mathematically this will look like this. So epsilon naught pi equal to closed surface integral E dot del delta A, that is equal to Q E and C enclosed. Okay, so take an example. Okay, suppose there is a positive charge and that is a negative charge, and electric field goes positive to negative. Okay, so let's take an example. We consider the four faces. Okay, so consider the surface 1 and another surface, that is surface 2, that is 3D surface actually. Okay, and consider that another surface 3, and final choose another surface. Okay, okay, that is surface 4. So 4 surface. So calculate flux all 4 surfaces. So flux, if I calculate phi 1 for first surface, that is a electric field outward direction, means the surface encloses a positive charge. So phi 1, that is equal to E times S1 is positive. Okay, and suppose you consider the area vector that is in that direction, and also electric field in that direction, okay, tangent at that point. So that is a E times S1 or surface means, okay, that is a A1 and cos 0 be the 1, and consider surface to consider the area vector in that direction and electric field uh, in that direction. So that is a opposite. So cos phi 2, that is cos 180 minus 1 E A1, inward piercing actually, that is outward piercing is positive, inward piercing is negative. We know that in previous class. And number 3, if phi 3, see that very carefully, the actual electric field inwards here, but same electric field goes outwards. If I added these two flux, so you get a resultant flux is 0, because this surface T, 0 charge enclosed by the surface. No charge enclosed by the surface actually. So no charge bounded here. So means no charge bounded here means flux 0. Okay, like in that cases. So in that cases also, here also, that is total flux is 0, means 0 charge enclosed by the surfaces. So that means phi 0. And number 4, you see very carefully, surface 4 Q4 cover all 3 surfaces actually. So means these are added of phi 1 plus phi 2 plus phi 3. If I added these 3, you get EA1 plus 0 plus minus EA2. If I say that both surfaces are the considered small surfaces are the same, so that is means we get a 0. You cancel. So here There is a positive charge and negative charge. So net charge enclosed by the S4 surface is 0. So here no charge enclosed by the surface S3, S3, no charge enclosed by the surface, and S4 no net charge enclosed by the surface. Okay, no charge, we see that very carefully, the diagram, no charge, no net charge means some plus or minus they cancel out each other. So get a no net charge actually. Okay, clear. So always important, the two charges are equal magnitude but in opposite polarity. The field lines that is represent that is net charge of electric field. So that means they cancel each other. Okay. Now derive Gauss law and Coulomb's law. Okay, Gauss law to Coulomb's law in electric. Gauss's law and Coulomb's law. Consider a sphere and that is a positive charge here, plus q, and that distance is r. We consider a very small surface here that is called a delta A. So if a positive charge enclosed by the Gaussian surface, this is a Gaussian surface, so this surface called Gaussian surface. So E obviously outward direction because that is a positive, and area A also that outward direction. Okay, so from Gauss's law we know that uh, uh, epsilon naught phi means E dot dA vector, that is equal to charge enclosed by the surface. You know that Q enclosed. So epsilon naught closed surface integral E dA cos 0 degree Q cos 0 be the 1 epsilon naught. So E dA Q enclosed. So epsilon naught E integration of dA, that is a Q enclosed, epsilon naught electric field E, and integration of dA is the A times Q enclosed, and that is E equal to Q by epsilon naught A. Okay, so what is the A? A is the area. Okay, if I that is a sphere, means we know the area of sphere is a 4 pi r square. So Q by epsilon naught 4 pi r square, that is 1 by 4 pi r square, that is Q by epsilon naught, that is equal to K, electrostatic force constant or Coulomb's constant, Q by epsilon naught, that is E. Okay, that is the Coulomb's law. Okay, you may divide by another charge, you may multiply this to the Q times E, that is the force, that is actually Coulomb's law. Okay, clear the Gauss's law and Coulomb's law. And if I that similar that electric phi to that bound extra, okay, that is doesn't matter, actually both are in same. Okay, if I similar derivation like this, if delta phi similar like derivation is like this, is a delta phi flux, that is a E dot delta A, and that is a E means you know the Q enclosed charge by 4 pi r square times uh, 4 pi epsilon naught okay, times r square. Here is a delta A, and there is a r cap direction. And if say the r cap actually that in that direction r cap, okay, the r cap and delta A both are in same direction, so means q enclosed by 4 pi epsilon naught r square, and that is also the same direction, so cos 0, so r dot delta A cos 0 degree, cos 0 you know that 1, so finally we get q enclosed by 4 pi epsilon naught r square. So we get r dot delta A. R is a unit vector. So unit vector, that is we know that is r equal to 1 unit vector. So that we get a q enclosed by 4 pi epsilon naught, that is r square times delta A. Okay. So that is a delta phi. If I put a limit, okay, and that is convert delta to d actually. If I put a limit here, integration, to get phi, so q enclosed for unit vector, so by 4 pi epsilon naught r square and delta A integration, that is delta equal to A. So finally we get q by 4 pi epsilon naught r square, get area A, and that is A is a surface, so sphere curved surface area is 4 pi r square, so cancel 4 pi cancel, we get phi equal to q by epsilon naught, that is phi means charge enclosed, ENC. So that is a QENC equal to phi times E. Sorry. Phi times epsilon naught. That is not E, that is epsilon naught. So today lecture start from actually these equations. Q enclosed, that is phi times epsilon naught. You see that the start from lecture these equations. Okay. Sorry, not a start from lecture actually. The Gauss's law start from these equations. Okay, sorry, ignore that. Okay, we clear the Gauss's law concept. Next class, the continuation of Gauss's law, some application. Okay, so today end the class here. Thank you.